Good morning, my friends. Welcome to our discussion of equilibrium constants. Today we're going to be talking about what equilibrium constants are, how to write what's called an equilibrium expression for a chemical reaction, as well as how to calculate equilibrium constants from data. All right, let's get started. So we know that equilibrium is established anytime the forward rate is equal to the reverse rate in a chemical reaction. At that point, no additional amounts of products or reactants are being produced. You're not losing any net reactants and you're not gaining any net products, even though the reaction is still happening in both directions. So you're constantly making products, but some of those products are constantly breaking back down into the reactants. Now you increase the concentration of any of the reactants and when it's at equilibrium, the speed of the forward reaction will suddenly increase. So you'll start making more and more product. Now as you do that, you consume the reactants. So the concentration of the reactant starts coming down and your forward rate starts slowing down. On the opposite side of that, as the reaction, when you spike the reaction with putting a bunch of reactants in there, you start making a lot more products. So the reaction rate of the reverse reaction started increasing because there was more products being made. So what's going to end up happening is the forward reaction rate is going to suddenly jump up, and then it's going to fall as it uses up some of the reactants. At the same time, the reverse reaction its rate is going to increase, and they're going to meet somewhere in the middle and reestablish a new position as soon as those two reaction rates are equal again. So we know that equilibrium reactions have multiple equilibrium positions depending on the concentration of the reactants and the products. And you should be able to take this explanation, we just did, from a spike in any of the concentrations and what happens to the reverse and forward reaction rates based on that increase in concentration or decrease in concentration of something. So you can explain how the reaction, the equilibrium shifts either towards products or towards reactants, as well as describe what happens to the rates. Let's consider this reaction. We'll model it real quick. Let's say we start out and we inject into a container some nitrogen and some hydrogen, and if they're catalyzed well, they'll make this ammonia. But then the ammonia tends to also break back down and turn into hydrogen and nitrogen. And so once these rates are equal, we have equilibrium, we get no new amounts. So if we go back to our beginning, we're like, okay, so we take a container of nitrogen, we inject it into a cylinder, at the same time we inject hydrogen. And let's say we do a 3-to-1 ratio to keep it easy, a stoichiometric ratio here. So what you might expect is all this to get used up and go there, but it's not, it's an equilibrium. So our concentration, let's draw our concentration of N2 first. And we're going to only put one in, so we're going to start with a fairly low concentration. And the concentration of N2 is going to decrease as it gets used up. Well, as it approaches equilibrium, it's going to level off, and that's going to become a constant concentration. Well, now you can see here that if this is used up at 1 mole per second, hydrogen is being used up faster at 3 moles per second. So it's going to have a faster concentration curve. It's going to be a steeper curve, but then it's going to level off as well when it reaches equilibrium. Now every point along the way, the slope of this line is 3 times steeper than this line because the reaction rate is 3 times steeper than this one. Now our NH3, as these guys are being consumed, it obviously is coming from a 0 concentration up to some new concentration. And I'm going to draw like this. So let me label these guys. I should have done this to start with. This is our H2, high concentration and fast reaction rate. This is our N2. We put less in, so we have a lower concentration and a slower reaction rate because you're using less in the reaction per thing. And then this one is NH3. It has a medium reaction rate, and it really should be twice this one and 2/3 of this one. I didn't quite draw it right. But at this point here, where the concentration stopped changing, this is where we're in equilibrium. This reaction situation will stay constant like this forever unless we change the temperature or we change the concentrations of anything. So if we inject more nitrogen, this one will suddenly spike, more forward reaction will happen, and it'll establish a new equilibrium. All right, so now if we look at the reaction rates of the forward and reverse reactions. So when we first squirt or stick the gas into the cylinder, right? So we first inject the cylinder, we're going to get a reaction rate that's forward that's really fast because it's going to be super high concentration. You can see here it's steep here. So we're going to get really fast reaction rate for the forward reaction. It's going to start up here somewhere really fast. And then over time it's going to decrease as we use up our good friend nitrogen and hydrogen. Is going to decrease the reaction rate. Now, it's going to continue decreasing, but as that decreases, or as it makes product, more and more product's going to build up. So at first, we're going to start with 0 reaction rate for the reverse, right? So let me label this actually forward. The reverse reaction is going to be starting out at 0, but it's going to increase over time, but it's going to taper off. This one's going to go here. And as soon as the reaction rates are equal to each other, this is the point of equilibrium. Now the reason the reverse reaction rate starts off slow and gets faster is because we don't have any product at first, but we make more and more product. So it goes like this and it levels up and it hits this other one, and now their rates are equal and we're at equilibrium. All right. This is kind of a tricky one, so I want you to give this a shot yourself. When sulfur reacts with oxygen, sulfur trioxide is produced in equilibrium. So let's say this thing starts out at equilibrium, so it's like this right now, and then someone ejects enough SO3. So we do this and we triple the concentration. I want you to discuss in your lab notebook, discuss with your group, and in your lab notebook, write an answer to this. Explain what would happen if we tripled the concentration of SO3 in terms of the forward and reverse reaction rates and the amounts of products and reactants. So those two big ideas. And it might help you also to sketch a concentration versus time graph and a reaction versus time graph. So what I'm going to do is I'm going to help you out with that a little bit, because if we start in equilibrium, we're not going to have these moving things. They're going to be straight lines to start with. So our SO2, maybe it's like here. Our O2 maybe is half that much. So this one's O2 and SO2. And I don't know, let's say that we don't know where the SO3 is going to be, but let's just say that it's more than both of them. That this equilibrium, maybe it favors the product, so you get a lot of product from it. So let's start with that one like that, SO3, SO2, O2, and suddenly, here's what it would look like. We suddenly spike the amount of SO3. So this line all of a sudden, stop doing that. This line all of a sudden jumps way up like this. So in a very short amount of time, it jumps up to some new high number. And now from here, I want you to sketch what the rest of the curve looks like for this one, and this one, and I'll draw these guys over just a little bit more. That's super annoying. All right. Now for the reaction rate, I'll help you here too as well. Since we start out at equilibrium, we know our forward and backwards reaction rate are equal. So I'm going to draw them right here. So there's the forward and there's the backwards, equal to it right on top of each other. So this is both the forward and backward. And at this point, you have to ask yourself, if we were to triple this concentration, what would happen to the backwards reaction immediately, and then what would happen over time to the forward reaction. All right, give that a shot. hit pause on the video and try and do that. Okay, awesome. So we're back. So let's take a look. It might be easier to start with this reaction rate one. If we suddenly spike this up, what's going to happen is the reverse reaction rate will suddenly increase. Because now we have all kinds of product to collide and go back to reactant. Suddenly increase. And then over time, let me say that differently. As products are used, products are consumed. Maybe consumed is a better word. The reverse rate slows. At the same time, as more reactants are produced, and maybe made's a better word here so producers get confused with products, but at the same time as more reactants are made, the forward reaction speeds up. So here's what happens. Suddenly the backwards reaction, the backwards reaction jumps up like this. And then as soon as this goes up, now it starts falling back down. And the forward reaction, as it falls, because this is falling back down because you're consuming the products. You have a whole bunch of products, so it's going really fast. As you use them up, you have less concentrated, so it slows down. But whenever you decompose these products into reactants, you just increase the reactant concentration, driving the forward reaction faster. So the forward reaction goes up like this. Goes up like this, and it levels off too. And when these two come back together again, now we're at our new equilibrium at a faster rate. So here's equilibrium, here's our disruption. So this is the addition of SO3. And we have a new reaction equilibrium position up here at the reaction rates. Our old one was here. Okay? So again, both rates increased. They meet in the middle somewhere. It's not exactly the middle. It depends on where it's going to be, but it's going to be in the middle somewhere. Now, in terms of concentrations, SO3 suddenly spikes. Over time, the SO3 is going to get used up, and it's going to decrease. So the exact shape of that decrease, we don't know yet. And as it decreases, we're going to get an increase in the SO2 and the O2. And at some point, these guys are going to balance out again. And it's going to fall across like this. And these guys are going to balance out and become constant and become constant. So at this point, we've reestablished equilibrium. And our concentrations are constant. Notice the new equilibrium position has higher concentrations for everyone. Because increasing the concentration of one is going to drive both of them to higher amounts or higher concentrations. All right, awesome. So that's the equilibrium stuff. Hopefully you can explain it in terms of rates as well as concentrations. Next thing we need to do is actually be able to write an equilibrium expression. So we consider this reaction below where we have A reacting with B to make C and D. These little letters here are the coefficients. So if this was a regular equation like 2H2O, or sorry, 2H2 plus O2 gives 2H2O, this little A would be that 2 in front of the H2. So these are the coefficients of the reaction. Now we know that the position of the equilibrium and the rates are not constant. They depend on how much concentration is in there. But there is something constant about equilibrium, and we call that thing the equilibrium constant, as you might be surprised. And the equation for it is here. So capital K is what we use, and you're going to love the fact that there's a lot of K's in chemistry, and they all mean different things, although they're all really similar, so it might even make it a little harder to figure out what's going on. But here, this lowercase c, so this is the concentration of one of the products raised to the power of the coefficient in front of it. And oftentimes this is a 1, no worries if it is. And this is the same thing, concentration of the D product raised to the coefficient in front of its power. And then the same thing for the reactant. So notice here that it's always products over reactants. And that's always true of our good friend, the equilibrium constant. It's never reactants over products, always products over reactants. Now what that means is if K is big, that means this number on top must be bigger than this number on bottom, and the equilibrium lies towards the products. Or you could say it as the equilibrium favors products. So if this number is really big, this K is really big, that means you have a whole bunch of products and very little reactants. That reaction would look like a only forward reaction. It would look like all the reactants got consumed and just made products. Now the opposite's true. If K is small, that means that the number on bottom must be really big. To get a small number like 0.0000007, that means the number on bottom must be really, really big. I think I might have just said that wrong just now. Really big. So the reactants are favored. So in that case, that's a reaction that stays over here, and very little product is made. Yeah, almost all it stays as reactants. Very little product is ever made. All right, I just wrote all over it. Let me go back and delete that real quick. So from the relative size of K, we can get a sort of a pretty good idea of whether we're going to get a lot of products from the reactants or a lot of reactants. We have to be careful on that because it's a little more complicated. We can't compare K's too closely. It's basically these big orders of magnitudes. So it's only if it's really big or really small. Okay. Now this expression up here has two names to it. It's called the law of mass action. You'll hear that for it. And it's also called the equilibrium expression. This second one, equilibrium expression, is more common, but the law of mass action you should be familiar with. All right, go ahead and give these two a try. Write the equilibrium expression for each, or the law of mass action, for each of these two reactions. So go ahead and pause the video and then come back when you're ready. All right, so let's do this together. So K, where's my thing? All right, so for this reaction, K is equal to, remember it's the products, there's only one product here, the concentration of NH3, and it has a 2 in front of it, so I know I have to square that, divided by the reactants. I've got the concentration of N2, and I got the concentration of H2. Those are my reactants. N2 is raised to the first power, 1. You don't have to write that if you don't want to. And H2 is cubed. That is the equilibrium expression. Now these can also be written, because they're all gases, these can also be written as partial pressures as well. So you can get a separate K called K sub P, which would be the partial pressure. It's going to follow the same thing of NH3 divided by the partial pressure of N2 and the partial pressure of H2. We still have to raise them to the power, so this one has to be squared. And this one has to be cubed. I'm going to draw some parentheses in here. And this one's to the first power. So there's two ways of writing the equilibrium expression. There's K in terms of concentrations and K sub P in terms of pressures. Don't worry too much about the pressure one. I just want to introduce it here. We'll deal with it a little bit more in the future. And this other one, real quick, let's do this one down here now. So we have K is equal to the products SO3 squared divided by the concentration of the reactants raised to their coefficients. So we have concentration of SO2 squared times the concentration of O2, and that's it. That's the equilibrium expression. Okay, so not all products and reactants are included in the equilibrium expression. The exception are pure solids and pure liquids. The reason they're left out is because their concentration can't change. You can't make the concentration of pure water different than the concentration of pure water. It's pure. So it doesn't get included. It just gets left out completely. The same thing with solids. So if we look at this and we have these two solids here, our equilibrium expression gets easy to write. You can't make calcium carbonate change its concentration. It's a chunk of stuff. It won't happen. Same with calcium oxide. So here our equilibrium constant we find only depends on the concentration of CO2. And since there's a 1 in front, to the first power. That would be our equilibrium expression for this reaction. It would not include these two. These two would not include, would not affect the equilibrium. Just the CO2 does. And this one could be written in terms of pressures as well. So the K sub P here would just equal to the partial pressure of CO2. All right, so we still need to learn how to calculate the equilibrium expression, and it's pretty straightforward if you have all the right data, right? So here's our reaction between nitrogen monoxide and chlorine gas, and then the equilibrium. We have some data about the equilibrium concentrations. Now notice these are the concentrations at equilibrium. That's critical. You can't use starting concentrations. You've got to wait till it's at equilibrium, then measure the concentrations to get K. We'll learn how to deal with starting concentrations later on in the course. It's a little more complicated, but definitely doable. Our first step is to write the equilibrium expression for it. So K is equal to, well, actually, pause the video and give this a shot. Let's see how many of us can do this right now. Write the equilibrium expression out, and then plug these guys in and see if you can't solve for K. All right, let's do it together real quick. So K is equal to the concentration of NaCl squared divided by the concentration of NO squared times the concentration of chlorine gas, and it's the first power, so there's just a 1 here. So that's our equilibrium expression. So if we come down here and we say, okay, so K is equal to the concentration of NaCl squared divided by the concentration of NO2 squared and Cl2. I know this, and this. I know all these concentrations. I can just plug them in to find K. Let's do that real quick. And my NaCl is this one. So I say, okay, so 0.181 moles per liter squared divided by the that should be NO. The NO concentration, which is 0.055 moles per liter squared, times the Cl2, which is 0.0013 moles per liter. And we do this math. This part's kind of interesting because people make a mistake on this. So it should be 0.181 divided by the one down here, 0.055. Whoops, I already made a mistake. So let's go back up here. So 0.181 squared, then divided by 0.055 squared. And what a lot of people do is then they go times this. But because this number's on bottom, what you're really doing is dividing it into that. So we want to hit divided by again, and then 0.0013, and we end up with 8,330 for 8,330. Now, by convention, we do not include any units on K. Even if there's units left over, we totally ignore units on K, and we express them on the equilibrium constant as just a number without any units. And you guys are going to love that, because I always tell you have to have units on everything, and here's a number where you don't have to have units, although it might be confusing to know when to and when not to do it. All right, so that's how to calculate K. Now, because K is such a huge number, we know that our products are going to be favored. This is a way bigger number, and we can see by the equilibrium concentrations. These are super small concentrations. This is a large concentration. So this equilibrium favors the products. It makes a bunch of products and consumes almost all the reactants in the process.